completing our final closeouts in inspections and testing, integrating the fairing, and rolling out to the pad, and then launch on December 18th. Once we get past launch, we have a 180-day period of on-orbit commissioning, consisting of a spacecraft phase where we have launch and ascent. We do a mid-course correction maneuver to get us on the proper trajectory to get out to L2. And then what you're going to hear about today are deployments. Once those are completed, we will kind of move into the mirror phase of the program, where we will deploy the mirrors. We align those mirrors to create the perfect image. At the same time, we'll initiate some of our science instrument activities, as well as finish our cooling down to our operating temperature below 50 degrees Kelvin. From launch plus 118 days to launch plus 180 days, we will commission our 4 science instruments. As I mentioned today, this panel will discuss deployments as well as some aspects of the science that JWST will do. And for that, I will turn it over to Begonia down at the launch site.
Thank you, Bill. I'm here in Kourou outside the viewing window in the clean room on the Space Center, where James Webb has been in its deployment configuration since its arrival. And here is where all the inspections, electrical testing, and mechanical activities to confirm everything is nominal after shipment have been completed. It will be here for about another week, and then, as Bill mentioned, it will be moved for its fueling. The James Webb was designed with very lofty science goals in mind. To look back in time 13.5 billion years to see the first galaxies that form in the universe and see how they change and evolve to get to the type of galaxy where we live in today. Also to look at the first stars, the first light in that universe, stars that were 300 times more massive than our sun, and that when they exploded as supernova generated radiation and the heavy elements that made us. James Webb will continue looking for planets around those stars, exoplanets, and will be able to look in the atmosphere of the planets to see if it detects the type of elements that we identify as a sign of the life that we know: water, carbon dioxide, methane. To be able to, as well as all these faraway objects, James Webb is also able to look in our neighborhood to look at planets, comets, and asteroids in the solar system. The light from these faraway objects has been traveling those 13.5 billion years in a universe that is expanded. So the wavelength has expanded too, and it has moved to the infrared. So to be able to take the images and spectra of these objects, we need to do so in the infrared wavelengths, which is a little bit different from Hubble that looked mainly in the visible part of the spectrum. Planets and stars are formed in parts of the universe where there is a lot of dust and gas, and again, visible wavelength is not able to look through. So that's another reason why infrared is the optimal wavelength for James Webb. Now, everything emits on the infrared. We can think of it as heat. So to be able to detect the faint signals of these objects, we need to be able to cool down the mirrors and the instruments. The instruments will be very close to absolute zero, only 40 degrees Kelvin above. That's about minus 385 Fahrenheit, minus 233 centigrade. And James Webb achieves these cool temperatures by having a large sun shield, as large as a tennis court, made of special material, Kapton, and 5 layers, that is too big to fit in deployed, so it needs to be folded to fit inside the rocket and will be open once we are on orbit. The other design driver for James Webb was to be able to collect more light to detect the faint signals of these objects. And we do this by having a large mirror that has 6 times the collecting power than Hubble did. Again, this mirror cannot fit in one piece, so it's made of 18 small mirrors that can be folded to fit inside the rocket. They are made of another special material, beryllium, that behaves well at cool temperatures and also can be made light. And the mirrors have a coating of gold, which is optimal to reflect infrared light. When we are at home, our mirrors are coated of silver or aluminum, which is optimized for our visible eyes. James Webb is going to be very far. Hubble orbits the Earth. James Webb is going to be 4 times the distance of the Moon, so we cannot service it. So lots of redundancy has been built into it as well. The instruments on James Webb are also state-of-the-art with state-of-the-art detectors. James Webb is an international collaboration, so one of the instruments that will be the guide and keep the observatory stable is a contribution of the Canadian Space Agency, as well as the science instrument for the near-infrared imager and slidless spectrograph. 2 of the instruments, as well as the launcher, the Ariane 5, are the contribution of the European Space Agency. So those instruments is a near-infrared spectrograph and a mid-infrared imager and spectrograph. And the final instrument is a contribution from the US and the University of Arizona, a near-infrared camera. As Bill mentioned, after launch, we have 6 months of commissioning, the first month dedicated to the deployments, which you're going to hear more about today. 3 months dedicated to the alignment of those mirrors. When we look at the star, the first star with James Webb, we will see 18 stars, and we need to make it a single one. And then 2 months dedicated to the calibration of all the science instruments observing modes. To tell you a little bit more about the design of James Webb, here is Mike Mansell.
Good morning. As Begonia has already told you, the science of James Webb demands a 6-meter class telescope. And with a primary mirror diameter of 6.6 meters, the James Webb will be the largest telescope ever put into space. It'll be over 6 times bigger than its predecessor, the Hubble Space Telescope, and have light collecting power over 44 times greater than a previous infrared telescope, the Spitzer. Now, aside from just the size, science also demands that the telescope be cold, because you don't want the telescope glowing brighter than the faint stars that it's going to look at. And that telescope has to be very cold, about 55 degrees above absolute zero, or minus 360 degrees Fahrenheit, all 3.5 metric tons of it. And the science instruments have to be even colder. They have to be around 40 degrees above absolute zero. To get to those temperatures, we built a sun shield that is essentially an umbrella that'll keep the telescope and the science instruments in the shade. But this sun shield is no ordinary umbrella. It's going to be irradiated by 200,000 watts of solar radiation. And it should only allow about 0.02 watts through. So if it were suntan lotion, it would have an SPF of about 10 million. And the way we do this is the sun shield is composed of 5 individual layers, each about the size of a tennis court. The first layer facing the sun will reflect most of that 200,000 watts that hit it. But of the small amount that gets through, that wattage, that power, will reflect back and forth between the first layer and the second layer until it eventually bounces out the edges. And that small amount of power that gets through the second layer will then bounce between the second and third layer and eventually go out the sides. So here we have this, the James Webb Space Telescope. When it's integrated with the telescope and the sun shield, we'll have an observatory that stands about 3 stories tall, is 6 metric tons. It's about the size of a tennis court, and the telescope will be below 55 degrees Kelvin. This is a very challenging mission. Now, you can see the telescope and the observatory have 4 major parts to it. First, the telescope itself that we call the OTE, optical telescope element, and it has that large primary mirror consisting of 18 individually controlled segments. Behind it are the 4 science instruments that are integrated into a common assembly that we call the ISIM, the Integrated Science Instrument Module. Then we have that big umbrella, the sun shield, consisting of 5 layers. And on the hot side of the sun shield, we have the spacecraft bus. And that spacecraft bus has the traditional spacecraft subsystems, electrical power, telecommunications, guidance and navigation, that kind of thing. So with an area of about the size of a tennis court, James Webb does not fit into the launch vehicles we currently have. And to fit into the Ariane 5 launcher, which has a 5-meter diameter fairing, we have to fold the telescope up. Well, let's fold the observatory up. And that means we have to unfold it on orbit, a very complex and challenging procedure. Now, when I started in this business about 40 years ago, I remember one of the first lessons I got taught was avoid deployments on orbit. James Webb cannot avoid the deployments. In fact, James Webb has to perform some of the most complex sequence of deployments ever attempted. And these come with many challenges, but I categorize the challenges into two broad categories. The first challenge is that many of these deployments are what I'd call precision deployments, particularly those of the telescope. Now, think of what we're doing here. We've built a world-class infrared telescope. We've built it, we've aligned it, we've tested it, we've proved it worked. Now we're going to have to break it up, fold it up, and actually rebuild it on orbit, rebuild it, realign it, retune it, and get it to work robotically on orbit. That's never been done before. And this rebuilding and this alignment are to optical tolerances. And to put that in perspective, what that means is any light ray through the telescope has to have an error no greater than 150 nanometers from its prescribed path. And if you want to know what 150 nanometers looks like, well, that's about 1/670th of the width of a piece of loose leaf paper. Now, the second set of challenges comes because a lot of these deployments involve floppy, indeterministic members like those big sunshield layers that we talked about. You know, NASA is used to deploying rigid beams on hinges because they're deterministic. You can control how they move. But these, when I say something is indeterministic, I want you to, that's illustrated by this example. Take a string and put it on a tabletop and push on it, and see if you can predict the shape of that string. Chances are you will not be able to, and so it is with the membranes of the sun shield. So we can't really predict their shape, but we can constrain it. We can try to prevent it from going in places that we don't want it to go, places where it could snag or tear or maybe impede the deployment of other members. And we do that by building in restraint mechanisms. And there's going to be a lot of these restraint mechanisms when you're talking something the size of a tennis court. We've done extensive studies, we've done extensive experiments to determine just how many of these release devices we want. You see, we want to have enough devices to control the sun shield, but not too many to add unnecessary failure modes. Now, we've done these exhaustive studies, and the answer we came up with was reviewed by various independent review groups. And in the end, we've all agreed we found the sweet spot on this. We found the right mix of mechanisms. The final part of the mission that I want to talk about that's a little unique is our orbit. We're not going to be orbiting the Earth. James Webb will operate around the Sun-Earth second Lagrangian point. Now, that's a point 1 million miles away from the Earth, 4 times farther than the Moon, on the opposite side of the Sun. It follows the Earth around the Sun every 365 days. And it's a point where the gravity of the Earth and the gravity of the Sun combine to make a relatively stable point. Now, our Ariane 5 launcher will put us on a direct inject path out there, and it'll take about 40 or 50 days to get out at that distance. And during that time, we'll do 3 mid-course corrections. We'll do our deployments that you'll hear more about in a second. And around 40 or 50 days after our launch, we will actually fall into a little orbit around the L2 point. By that time, we will have cooled down, and we will be calibrating our instruments. And at launch plus 180 days, the observatory will be commissioned, and we'll be ready for our science mission. And during that science mission, we will execute an orbit around the L2 point that takes about 180 days. Now, because the L2 point is only close to stable, we have to do station keeping maneuvers to stay in that orbit, and we'll do station keeping about once every 21 days. And now to talk more about the deployments, our deployment systems lead, Alfonso Stewart, will come up and give a better explanation of some of these.
Thanks, Mike. Here at the launch facility in French Guiana, helping to prepare Webb for the integration to the launch vehicle. You've heard about the science goal from Begonia and the overall design of Webb from Mike, but what I'm going to talk about is the nominal deployment sequence we're going to go through in order to achieve the deployed state. So what is origami? Like an origami object, proper folding and unfolding is necessary in order to achieve a specific shape. And Webb will do origami in reverse, meaning that it will unfold in a certain sequence. Now, you may have also heard the reference 29 days on the edge. And what that means, there are 2 important times in that deployment scenario. There's the launch And also at L plus 28 days, there's the thruster burn to insert Webb into its operational orbit. The timeline we're going to talk about today is the nominal timeline. However, we do have the flexibility within that timeline to adjust if necessary. Now, at the start of deployment, the predicted temperature is approximately 20 degrees C, about room temperature. However, over the deployment timeline, the temperature will decrease down to negative 200 degrees Celsius. The first deployment the first set of deployments are the solar array and high gain antenna. So why the solar array first? Well, electrical power is required for the observatory to function, and the battery can only last a few hours. So we need the solar array to be deployed in order to continue with the mission, and then followed by the high gain antenna for the necessary communication capabilities in order for us to continue the commissioning activities. In preparation for the Sunshield deployment, the UPS or unitized pallet structure, deployment tower assembly, and the trim flaps are deployed. Then we start the Sunshield deployment sequence. That sequence starts with the membrane cover release as shown here in the graphic, followed by the mid-boom deployment that pulls out the membrane in radiator shade. Next, we have the OTE assembly that deploys the secondary and primary mirror assembly. Now, in addition, as I mentioned before, this is a nominal deployment sequence that we're planning. However, Webb uses contingency operation in the event of an anomaly deployment action. Now, these operations range anywhere from the simplest, such as checking the telemetry and resetting the command, to the more complex operations such as switching to the redundant system, or we can also use what we call excitation of the observatory, what we aptly name shimmy, twirl, and fire and ice. And now we have Crystal Puga that will describe the most complex of these deployment in further details. Over to you, Crystal.
Thanks, Alfonso. I'm here in the launch site control room in the satellite processing building in French Guiana. This is the room where Webb engineers will monitor the observatory's state of health on the day of launch using the telemetry you see on the screens behind me. So as the other speakers mentioned, the sun shield is a critical part of the observatory. It has one simple task. It needs to protect the observatory by blocking the heat from the sun, the earth, and the moon. Although it's a task, it is worth diving deeper to truly understand the truly pioneering system and how the sophisticated umbrella works. The sun shield separates the Webb into the hot and the cold side. On the hot side of Webb, it is a toasty 260 degrees Fahrenheit. Meanwhile, on the cold side, it's a freezing negative 300 degrees Fahrenheit, which is colder than any place on Earth. That's a roughly 600-degree temperature differential, which is accomplished passively using 5 tennis court-sized sun shield layers made out of a special material called Kapton. Kapton has unique thermal properties that are needed to keep Webb cold. It's highly resistant to heat and remains stable across a large temperature range without burning or melting. On Earth, Kapton is typically used as an electronic insulator and is actually a translucent amber color. So in order for us to accomplish the heat radiation bouncing technique that Mike described in an earlier section, we first need to enhance the Kapton even more. First, we coat it with an aluminum on both sides, which makes the membranes reflective, allowing for that bouncing and for the heat to be able to reflect out in between the layers. We also apply a silicone treatment, which is applied on the sun-facing side of the 2 hottest layers, which is the silicone is actually even more effective at radiating the heat back into space. This also gives the sun shield a soft purple color that you see on the bottom of several of the images. The sun shield Kapton material is super lightweight, and in fact, it's really thin. It's only about the thickness of a human hair. And I have a sample here with me. You can see the sample. It's very crinkly, and it's very, very thin. In order for us to construct the sun shield, we actually put it together like a quilt using patches of this Kapton that we thermally bond together. So you can see a bond here, thermal bonds, putting 2 of these pieces together. Those bonds create about 10,000 seams. Each layer has a unique template because each layer is actually slightly different in size and in shape. To strengthen the membranes, we actually add reinforcement strips about every 6 feet. These reinforcement strips act as ripstops to help eliminate or contain any tears or holes that are caused by micrometeoroids. The metallic ribbons also help to provide structure to the membranes. Before we get into the sunshield deployment, we first need to address the stowing process, which is just as critical. The sunshield has to be packed away to fit inside of a 5.4 diameter rocket fairing. The folding process has a very specific sequence. First, we carefully fold back and forth accordion style using engineers that are fully trained and know not to handle the material very delicately to avoid any creases or tears. They also use a specially designed folding fixture to allow them to do that. After we fold each sunshield membrane, we then fold it up in between around all of the sensitive telescope and optics. So we need to make sure that when we deploy, we don't accidentally snag on any of those sensitive components. Our sunshield is very similar. It's our lifeline, similar to like a skydiver's parachute. It needs to be folded perfectly so that it unfolds and deploys perfectly without those snags, without any tangles. Now to the sunshield deployment. I think of the sunshield deployment similar to like a Rube Goldberg machine in that it uses a series of reactions that work in successions, triggering one event after the other until the entire sunshield is fully deployed. Some of the key hardware include 140 release mechanisms, about 70 hinge assemblies, 8 deployment motors. We have several bearings, springs, gears. About 400 pulleys are needed and 90 cables totaling 1,312 feet. The sunshield deployment starts on day 3, just after we pass the moon, and it will take approximately 3 days to fully complete. First, we're going to release the large pallet structure that holds the membranes. We'll do the forward side and then the aft. Next, we're going to release the special restraints that hold the protective covers and roll them out of the way. Next, we're going to release a set of covers that are on the core region. At this point, we're ready to actuate the 140 release mechanisms, which all must work perfectly. They're all single point failures. They all need to work perfectly in order to release the sunshield. 2 large motor-driven telescope structures called mid-booms will extend the sunshield in the horizontal direction, revealing the iconic diamond shape. The very last step is super important. We need to tension all of the membranes using a series of pulleys and cables to create that separation between each of the 5 layers. To perfect this sunshield deployment sequence, we performed multiple deployment testing over several years on both small and full-size models. We practiced not only the deployment, but also the stowing process. We have a very program. This gives us the confidence that Webb is going to deploy successfully in orbit later this year. So with that, I will turn it back over to Laura for Q&A.
Thanks, Crystal. Now we're opening our line for questions. If you're watching this on your device at home, would like to ask a question, be sure to mute your device before asking your question. Operator?
At this time, if you'd like to ask a question, please press *1 and clearly record your first and last name. Again, that is *1 if you have a question at this time. Our first question comes from Bill Hardwood.
Small and full-size models.
Yeah, thank you very much. Making sure you can hear me okay?
Yep, we can hear you, Bill.
Okay, yeah, thanks. I'm curious as to what the limits are, temperature-wise, to still have a successful mission. And what I mean by that is, if all the layers don't fully deploy and separate exactly as planned, can you still do science if 2 layers are touching, for example? Or if it gets hung up somehow, like can the near-infrared instrument still collect valuable science, even if you don't get a full deploy? If somebody could talk about those scenarios, I'd appreciate it. Thanks.
Sure. That's a great question for Mike.
Yeah, we do have some tolerance to that. One of the things that we've insisted on during the design of this is a cryogenic margin, heat rejection margin, and right now we're flying with about 80% of cryo margin, meaning we could anticipate, we could have unknown heat loads, for instance, about because of the layers touching. Now, we wouldn't want all the layers to touch, but if it's a localized touching in one place between 2 layers, that shouldn't be a problem for us, and that should only consume something of around 10, 15, at most 20 percentage points of our margin. So for the near-infrared instruments, I don't think that would be a problem at all. If it was more global contact, then if we started to eat significantly into that 80% margin, then we'd start to have a problem. But for our near instruments, that would the degradation would be graceful. And I don't have an exact number for you in terms of temperature on that, but I would suspect that detector temperatures probably, of around anywhere between 45 and 50 degrees Kelvin could still be tolerable to our mission in the near infrared.
Thanks.
Our next question comes from Marcia Dunn. Your line is now open.
Yes, hi. I have some questions for Mr. Metzel again. Certainly, the sun shield deploy. Correct me if I'm wrong, but it certainly sounds like the tensest, most hairiest, the most hairy part of the whole deployments. Is that true in your mind? Is this really going to be the most dramatic part of the whole early part of the mission? And how much of a gap is there between the layers? I'm wondering, it's the size of a tennis court, but how thick, if I were looking from the side once deployed, how thick would this be? And lastly, if I'm looking at this tennis court size sun shield, do you have to have at least, would you guess, half of it deployed properly in terms of, how the perimeter? I mean, just 3/4, or is it, or can you not really specify? Thanks.
Okay, well, first, to your first element, yeah, of all the things that, that I'm, I guess I don't want to say worried about, but the things that we focused on for deployments, it's definitely the sun shield for reasons, at least my personal reasons that I've already elaborated on. The sun shield is one of these things that is almost inherently undeterministic, unlike the things on the OTE where, once again, we have rigid booms that are on hinges and latches that we know how to control, although we've certainly focused on that. So the sun shield is the one that, has some risk to it, and we've certainly tried to concentrate on that. In terms of your other question as to the different failure scenarios, it would be, I don't think that I would say that if half of it didn't deploy, we wouldn't have a problem. We certainly would. As to, if portions of it didn't deploy exactly the way we wanted to, a lot of that would depend on where the misalignment was. But as I said, we have a cryogenic margin for some of that. And if the imperfection was localized, let's say to something around 12% of the perimeter didn't have the gap we want, we would probably be okay with that. As for the exact gap as for the exact dimensions between the gap, I think I might see if Crystal might want to answer that. I think it's of the order, the largest gap we have might be of the order of about 0.8 meters, or somewhere between 1.5 meters, if Crystal would want to correct me on that.
Yeah, so we do have a separation about 16 to 18 inches in between the layers. It actually, the distance varies because if you look at the photo of the James Webb, it's actually closer. In the core region, there's actually a smaller gap. And as you extend out towards the edges of the sun shield, the gap gets a little bit bigger. And this helps, again, with kind of that bouncing of the heat in between to radiate it out, which is why it's a little bit wider on the edges.
In the meantime, while we're waiting on the next...
Our
sorry.
next question comes from Chelsea Goes. Your line is now open.
Thank you. Chelsea Goes with space.com. As you've all illustrated, Webb clearly has a very complex deployment ahead of it. Could you talk a little bit about the kind of contingency plans you have in place? As I assume any anomaly at any of these stages of deployment would require perhaps multiple contingency plans, and how much pressure is on the team to get this right?
That's another good question for Mike.
Well, we do have multiple contingency plans, and I'll turn it over to Alfonso to talk about some of them in detail. Some of these plans have been pre-formulated for the more, time-critical deployments, and there's only one deployment really that's time-critical, and that's to get the solar array out. So we have some pre-formulated, pre-canned deployment plans, or contingency plans for that. For the other type of deployments, I'll talk to Alfonso a little, or I'll hand it over to Alfonso to talk a little more about that.
Yeah, thanks, Mike. Yes, there are numerous deployment operation or contingency operation that we have. And as I mentioned before, The contingency range anywhere from the simplest to the more complex. And I mentioned as an example, you can simply send the command again. Also, there are quite a bit of redundancy in the system. We have multiple ways of sending the same signal. In some cases, it's just a telemetry. In order to know that you have an anomaly, it could be just you have an erroneous telemetry. So we have redundancy telemetry, or we can check and verify a telemetry through other means. So there's quite a bit of redundancy. In addition to over the past years or so, the team have been practicing these contingency scenarios where an anomaly is introduced and the team will work to try to solve it in a sort of rehearsal plan. So both the design from in terms of redundancy and features in the mechanism, as well as procedures in the way we operate and the way we deal with these, we have been practicing and using and exercising those systems over the year to anticipate and to deal with these anomalies if they come up. So yes, we have been practicing quite a bit for that.
Our next question comes from Stephen Clark. Your line is now open.
Thank you for taking the question. I think my question is probably for Mike or Alfonso. Are there any areas in any of the deployments where there could be a single point failure? If there's an area where if something doesn't work, it would be very difficult to recover from that, like a mechanical structure or an electrical system or anything like that. And also, the deployments of the mirrors and the sun shield, do those, I know you said you have some flexibility in the schedule, but do they have to happen before you get to L2, or could you, push that weeks, beyond the scheduled intended date if necessary? Thanks.
Let's start with Alfonso.
Yes. Let me take the last one first. I believe the question was about do we have flexibility in the schedule for the mirror deployments? Yes, we do. The nominal deployment sequence is that we start the mirror deployment over approximately a 9-day period at around L plus 14 days. However, that deployment can occur much later into the program, even after the second burn at L29. So we do have quite a bit of flexibility in the mirrors. Now, I think the first question you asked about other flexibility we have or single point failures. Yes, we have identified single point failures on the system, and once we've done that, we have very detailed and extensive testing and review of the design, and just to make sure that these things the reliability are such. But there are single point failures on the system. I don't remember the quite number. I think Mike, if you remember the numbers, but there are quite a bit of single point failures. Single point failure system on the observatory. But we have identified those, and we have developed really rigorous test plan and operation procedure to deal with those. Yes.
Well, only as Alfonso alluded to, when we identify a single point failure, we give it very special treatment. We have what we call a critical item control plan, and we always throw in extra inspection points, and we've done extra offline testing on these devices. For each item that we've identified as a single point failure item, we do detailed analysis, and that includes testing, to identify all the possible ways that it could fail, and to make sure, for instance, if we know one of the ways it can fail, we add in extra inspection steps and extra tests and extra screening to make sure that probability of its failure is extremely low. So we've given our single point failure items a lot of attention, because when it comes to deployments and mechanical things like deployments, it's very hard to not have single point failures in them. And that's one of the reasons why we take our deployments, these deployments, as a very, very serious matter.
Okay, let's go to our next question.
Our next question comes from Paul Brinkman. Your line is now open.
Hi, yeah, this is Paul with UPI. I'm wondering if, I guess, kind of a follow-up to what Alfonso has been saying. You mentioned sending commands during the deployment.
I think we just lost Paul for a second. So we have a question from Rosie on Twitter. When is it going up? Bill?
So the launch date is December 18th, about 9 o'clock in the morning or so, Kourou time, which at that point will be 2 hours ahead of East Coast time.
And then the follow-up question from Alex on Twitter. Most telescopes are enclosed by a tube. Why doesn't the Webb telescope use that? Mike?
Yeah, that's an excellent question. The reason for that is due to the thermal. A tube around the telescope would actually impede its cooling. So we couldn't have a tube around it, which causes us, obviously some risks with stray light. But we've put in light shields at various places to preclude that. But the bottom line is we don't have a tube around that telescope, because if we had a tube there, it would actually impede its cool down to the 55 degrees Kelvin that we want.
Okay, next question from our operator.
Next question comes from Jeff Foss. Your line is now open.
Good morning. For the SunShield deployment, I'm curious what sort of instrumentation you have to monitor the deployment, the ability to stop or even retract the deployment if you detect any sort of snagging or tearing or other problems as you try to deploy the SunShield. Thanks.
Crystal?
Yeah, so we do have telemetry. We have read switches and telemetry switches that will allow us to determine when some of those deployments are made. In terms of being able to have the ability, some of the motors that are used, we can retract them, we can turn them back if we need to do any adjustments.
Okay, next question.
Okay, our next question comes from Lauren Grosh. Your line is now open.
Hi, thank you so much for taking my question. I was wondering if you all have an unofficial point during the deployment process that you've agreed upon you'll breathe a sigh of relief. I'm wondering if that is the SunShield deployment or if there's more to come after that that will be a sigh of relief for y'all. And then I'm curious, what is the protocol if you do realize that there is a showstopper failure, and what do you do if that ends up happening? Thank you.
Bill?
Let me try taking it. So I think I'll answer the first question first. Where we all breathe a sigh of relief is going to depend upon who you're talking to. As the project manager, I won't breathe a sigh of relief until we declare we're operational 180 days after launch. From a deployment standpoint, it's when all deployments are completed. We do have procedures set in place where if we start having issues that are extracted for a long period of time, we will go through a process of really narrowing down in on the problems. This team, one of the things, I've been a project manager for almost 11 years, and this team does not give up. So we don't talk about what do we do if we fail. We talk about how we correct problems that we see on orbit and how we move forward from there.
Okay, next question.
And as a reminder, if you'd like to ask a question at this time, please press star one. Again, that is star one. Our next question comes from Jonah Abels. Your line is now open.
Hi, thanks very much indeed. I think this might be a question for Alfonso. He mentioned excitation and shimmy. If there's a problem in the deployment of SunShield, I wonder if he could explain to us when and how he would dance with the stars, so to speak.
Yeah, I like that analogy, dancing with the stars. So let me explain. Again, that's a contingency. It's sort of like the very end of what we would normally do. And those that excitation contingency is basically, if you can imagine, you are exciting this observatory. And when I say, for instance, shimmy, you're rocking the observatory back and forth. So for us to do that, we would have to determine that will it really work, depending on what the failure is, and there'll be quite a bit of investigation to find out whether or not that particular system will work. Now, in terms of twirl, just like it says as twirl, we basically can spin the observatory about any given axis. And for fire and ice, what that's referring to, we can orient the observatory in such a way to put sun or heat up certain areas that we need to if we deem that that's necessary for the deployment. So that particular exercise of that contingency is probably the last ditch. Again, like I said, we have quite a bit of alternative contingencies in the system, such as redundancy and multiple ways of sending the same commands. So hopefully we don't have to use that one. Thank you.
Our next question comes from Marina Korn. Your line is now open.
Hi, can you give us an exact number for how many single point failures exist in the observatory overall? I've seen 307, 344. Do you have an exact number? And two quick follow-ups. Does this observatory have more single point failures than any other NASA spacecraft? And why are there so many? You said that it's hard to avoid so many for this kind of mission, but why is that? Thank you.
Mike?
Yeah, there are 344 single-point failure items on this observatory. That's the correct number. The reason for that is approximately 80% of those are associated with the deployments and are associated with the fact that we have mechanisms. It's hard to avoid, when you have a release mechanism, it's hard to put full redundancy into that. It's hard to compare it to other missions. I've tried, and there are two things that make the comparison a little hard. First, we have a lot of release mechanisms, and I tried to emphasize the fact that we tried to decrease that, and we found the sweet spot between getting the control that we want for these large, flexible membranes, and still, not or not putting more single-point failures on there. So we've done extensive studies on that, and as I said, I've tried to compare this to other missions. And the other thing that to bear in mind is very early on, our review boards wanted to make sure that we really took good attention to that. So when we counted our single point failure items, and when I give you 344, those are individual single point failure items. Some other missions count them slightly differently or count them a little less conservatively. We've been very conservative on this, and our review boards have actually lauded us for the fact that we've paid this much attention to it. But when you're talking about release mechanisms, mechanical release mechanisms, it's usually pretty difficult to avoid an item that we considered a single point failure item.
Our next question comes from Paul Brinkman. Your line is now open.
Hi, can you guys hear me? Hello?
Hi, we can hear you.
Oh, okay. I guess I'm kind of following up on something Alfonso said. To what extent is the process automated or robotic? And you mentioned sending commands, so I'm wondering how many times during the deployment do you have to send those commands if everything is going perfectly well? And I'd also like to hear, to what extent the eventual operation is robotic. And compared to Hubble, is James Webb more independent in terms of its operation, or is that kind of identical to Hubble? Thanks.
Alfonso?
Yeah, thanks for the question. For James Webb, the solar array and the initial release of the deployment radiator, the aft deployment radiator shade, or ADIR, is the only sort of automatic release system that we have. The rest of the deployments are all ground command, meaning that we will take our time and we send the command from the ground and wait for confirmation via the telemetry. So that all of the deployment after the initial deployment of the solar array are ground command, which we take our time to do. Did I answer all your questions? I don't remember. Yeah.
I just asked about operations also. That might be better for Begonia to answer. Is James Webb kind of more autonomous than Hubble is, or do they operate sort of similarly in terms of finding targets for investigations, I guess?
Yeah, James Webb is a little bit similar to Hubble. So once the once the targets are selected, right, an instrument wants to observe a particular target, those are loaded on board. A particular guide star is found that will achieve the target needed. and those are loaded on board and they run autonomously once they are launched. During the commissioning period, we do it step by step as we again take our time. So there is a very careful set of activities that we will be doing, and they are generated on the ground, loaded on board, and launched. We get the data, we confirm it's good, and continue. But after the 6 months of commissioning, the plans will be structured for the different science programs, also in a way to avoid unnecessary slewing of the observatory in an optimal way, and those can be loaded continuous weekly to proceed.
Okay, thanks.
Thank you. Next question.
Next question comes from Bill Hardwood. Your line is now open.
Hey, thank you very much. Just a question for, I guess, Mike. You know, we've all focused on the sun shield, and that's an obvious thing to focus on. But could you talk a little bit about the complexity of aligning the optics, how each of the mirror segments has, you know, the motors that can reorient them, can change their shape slightly, and how you go through that process of moving from 18 images of a star down to one tightly focused image? Thanks.
Yeah, I think at the next briefing we'll go into more detail on that. But I will tell you that our optics team, in particular our wavefront sensing and control team, has formulated a very methodical approach to taking those initially the 18 individually blurred images that will come from each segment and coalescing them into one image and then refining that to get one diffraction limited image at 2 microns. We have a very definite way of doing that, and we've tested that way several times on various test beds. One of them, called the telescope test bed, is a small version of James Webb. It's essentially an optical telescope, but it has 18 individual segments that the team has practiced alignment on. And I think you'll hear more about that when we get our optics leads up here for the next briefing. But there is a very methodically, well thought out, and well practiced wavefront sensing and control procedure that will take those 18 blurred images using the 7 degrees of freedom on each mirror. The 6 of them are the right, left, up, down, in, out, and then we have with tilting in the 3 directions, and then we actually have a 7th that can actually alter the shape of the primary mirror segments a little. So they'll utilize that along with actuation on the secondary mirror to get that final refined diffraction limited image at 2 microns. So, but the one takeaway I would say is that has been practiced on various test beds, one of which we call our telescope test bed. That is a miniature telescope with 18 individually controlled segments.
Thank you. We have a question from social media. This is for Crystal from Alan Smith on Twitter. Why is each sunshield layer such a complicated shape? Why couldn't each layer be a simple plane?
Yeah, so, we were trying to, in the way that we were designing the sun shield, right, we're trying to obviously cool it to get it to very cold temperatures. So each layer, the bottom layer, we wanted to actually block more of that's coming from the various heat sources. So it actually has to be a much larger shape at the bottom. We can get away with making them slightly smaller as we go in. So we didn't necessarily need to make them all the exact same size. And then I think actually I'll pass it over to Mike to elaborate a little bit more on that.
Yeah, when it comes to the question of why it couldn't be one plane, that was one of the very early trades that we all looked at. And it turns out by making it almost a biplane, as you can see, it kind of looks like this. That helps us with the way momentum is accrued, angular momentum is accrued. By tilting, when we tilt the telescope to various attitudes, the solar radiation vector, the pressure vector from solar radiation, and our center of mass and our center of our inertia can become misaligned. So by putting 2 planes in there, we can actually accrue less angular momentum for various attitudes. So that was the first question. And as for the shapes, we did want to tension the membrane. So part of that shape comes as a result of the tensioning and the fact that we want a gap at the edge, and we don't want as much of a gap where we anchor it. So part of that was a natural consequence of those boundary conditions. But when it comes to why we have two planes, it's essentially to try to minimize angular momentum accrual over the various attitudes that we will be scanning to.
Let's go to our operator.
Our next question comes from Marcia Dunn. Your line is now open.
Yes, from Mr. Metzel or Oaks, either or. I'm curious. Once the sunshield is deployed, how vulnerable is it to bits of space junk, micrometeoroid? I mean, is this going to be something daily that you're always worrying about to ensure that it's not damaged somehow? And I know that the spacecraft will be impossible for astronauts to reach. However, if SpaceX or somebody came up with some kind of mission to try to salvage it, is this spacecraft even repairable by human hands if you were able to get someone there in an emergency situation, or would that just be impossible the way it's designed? Thanks.
Yeah, I'll answer the micrometeoroids. I don't have the exact numbers with me, but we anticipated micrometeoroid degradation on both the sun shield and the primary mirror. We've accounted for that, and I don't have the exact numbers, but we do know we did hypervelocity experiments at Auburn University in the early days of this to see what kind of damage a micrometeoroid would do. And luckily for us, given the velocities that we expect from these things, the micrometeoroids, when they hit the mirror, will put nice, well-defined little bullet holes in it that'll really just detract from the collecting area. And when it comes to the sun shield, when they hit one of the layers, the micrometeoroid will pretty much disintegrate upon its first impact, and the debris will go out and maybe strike the next layer. The good thing about it is it's very unlikely that one micrometeorite will put a bullet hole in line through all 5 layers. That would be a bit of a pain, because then sunlight could make its way through. When it comes to your other question, as for serviceability, I will give that to Bill to answer.
So we get asked that question quite a bit. I think there's a couple of things folks need to remember, and I worked on Hubble for close to 20 years. Hubble was designed from the get-go to be serviceable. We have not been designed that way. There are aspects of us where you could not go in and change out an instrument. Our instruments are intertwined together. You cannot easily go in there and remove those instruments. There are other aspects that might be, if somebody was ingenious enough to service. Maybe there's some boxes that we might be able to get to, but there's no boxes on the outside of the spacecraft bus. They're all on panels that are folded on the inside, so that would make them difficult to get through. The one thing that we have done is our limiting resource is fuel. And right now we should have fuel to go 10, maybe even 10 plus years, out to even 13 years. We have put targets around where the fueling is, and have made the fueling, let's say, for lack of a better term, the gas tank is available. So if somebody was ingenious enough to get up there and try to refuel it, they would be able to refuel it.
Thank you. We have a question on Twitter from Venkata Sai Teja. What's the first priority task of the Webb telescope? Exoplanets, distant stars, or anything else? Begonia?
Well, the early release science programs have already been identified, and they cover all the aspects that we mentioned before. So there are observations on the solar system. It will be the Jupiter system. There is observation for distant galaxies, for stars, black holes, etc. And the intent of those early observations is to cover all the observing modes of all the instruments to showcase the capability of James Webb. And then after that, I think as you probably already know, the first year of operations has already been adjudicated as well, again, covering a large range. Now, each of the instruments, as we run through commissioning, they will have certain milestones when they know a particular mode is ready, whilst they continue to commission the other modes for that instrument. So there will be some play in there, but the idea is to cover all the possible observations that James Webb can do.
Thank you. We have another question from social. Connor Williams on Twitter asks, will there be another successor to the Hubble Space Telescope followed by the James Webb Space Telescope? Bill?
So right now, the next one is the Nancy Roman Space Telescope that's currently being constructed at Goddard Space Flight Center. Sometime in the near future, the Decadal Survey will release what their recommendations are as follow-ons to JWST. So really, there's no one here who can really predict that right now. They're looking at various missions and making the evaluation based on science of what those should have priorities, which of those should have priorities.
Thank you. We have one more question from the media.
That question comes from Stephen Clark. Your line is now open.
Thanks. I think my question is regarding the decision not to put cameras on the observatory to monitor any of these deployments. I know that decision dates back some time, but in hindsight or with modern technology, do you wish you had put cameras on, and would that really offer any insight into any sort of anomaly with any of these deployments? Thanks.
Mike?
Yeah, we've labored over that for many years, and frankly, I don't regret the decision, but it was a tough decision, and here's some of the factors that went into it. First, we could put some cameras on, and the first thing we asked ourselves is, well, what do we want to see? And and where do we want to look? And we found that the range of places that we wanted to look were all over the observatory. So now you could solve that by saying, well, let's put a wide camera on there. But that wouldn't really help you diagnose something that's really going wrong, like a snag. So let's put a high magnification camera on there. Well, then you got to put a lot of them. And where do you want to put them? Well, the majority of them are ended up going to be on the cold side. So now you've got cameras on the cold side, but when the sun shield deploys, it's going to be dark there. So now you're going to put lights on the cold side. And now you're going to be putting all the wires that go over to the cold side on there, and that's going to add parasitic loss. That's going to help heat leak from the hot side to the cold side. So, and then after the thing gets down to temperature, you need cameras that can passivate, or the cameras that can tolerate temperatures in the 55-degree or maybe lower region. So when we started summing all this up, summing all these cons against the cameras, against their benefits, we found that it really, we were in a land of diminishing returns where we really weren't getting all the benefit we'd want from these cameras, but we were getting a lot of extra nagging problems that we'd want to go along with this. So, it was a tough decision, and we've re-looked at it over the years, and each time we re-looked at it, the cons seem to outweigh the benefits, and that's the short story on this, but it is a good question and is one we've labored on over the years.
Thank you so much to our team here and in French Guiana, and thank you to everyone watching for the privilege of your time today. If you'd like to follow more news on the Webb Telescope, go to web.nasa.gov or follow the hashtag NASAWebb. Have a nice day, everyone.